We'll finish section 7.3 by solving the following differential equation. Let's solve y prime plus y equals to f of t, where f of t is defined by the piecewise defined function 0 when t is between 0 and pi, and 3 cosine of t when t is greater than or equal to pi. For a problem like this, usually we would begin by finding the Laplace transform of both sides, but we can begin actually, because we have our piecewise defined function f of t, we can actually start by writing this in terms of a unit step function, so we can have a single expression for our differential equation, as opposed to when we may have encountered a problem like this similarly earlier in the class, when we actually had to break it apart into two pieces and consider two separate ODEs. We know that the function is 0 for t between 0 and pi, so we can kind of ignore that part. That's just going to be 0. But then we want the 3 cosine of t part to turn on when t is greater than pi, which means we need to multiply that by the unit step function t minus 3. Now that we're here, we can go ahead and take the Laplace transform of both sides. We know that the Laplace transform is linear, so I'm going to skip a step and just go ahead and apply it to each term individually, factoring out constants as we go. So we get to this. We recall using our previous Laplace theorems that the Laplace transform of y prime, this is s times y of s minus y of 0. The Laplace transform of y, we call that y of s, is equal to, and now this thing here, so this is going to be 3 times the Laplace transform of the cosine of t times the unit step function of t minus 3. This is the result that we got when we did example 8. And if you recall from example 8, this should be equal to negative s divided by s squared plus 1 times e to the negative pi s. So we've already kind of worked that part out from before. So this is going to give us negative 3s divided by s squared plus 1 e to the negative pi s. And I forgot to write it, but in this problem they say that this prescribed value of y at 0, they want that to be equal to 5. So we have s times y of s minus 5 plus y of s is equal to negative 3s divided by s squared plus 1 e to the negative pi s. We now want to take this and solve it for the Laplace transform y of s. To do that, I'm going to do 2 steps in once. So I'm going to add 5 to both sides, and I'm simultaneously going to factor out the y of s on the left-hand side. That should leave us with a s plus 1 times y of s, and this is going to be equal to 5 minus 3 s divided by s squared plus 1 e to the negative pi s. And then to get the y of s by itself, we have one more step. Let's divide everything by s plus 1. Divide by s plus 1, divide by s plus 1, divide by s plus 1. When we do so, we find that y of s is equal to 5 over s plus 1. I'm going to leave this coefficient of 3 out for a moment. And then this becomes s over s squared plus 1 times s plus 1 e to the negative pi s. The last step, and it's just the last step, is to find the inverse Laplace transform of both sides. But before doing so, we want to apply partial fractions to this rational part that involves s. So we have this s over, this will be a separate part. So we have s over s squared plus 1 times s plus 1. And ultimately, when we write it, we don't want to forget that it's also multiplied by this negative 3 and this e to the negative pi s. But we want to break this apart so we can do the inverse Laplace. We have an irreducible quadratic factor s squared plus 1, which means we would have an as plus b in the numerator. And then we have our linear factor s plus 1, which would have a constant term in its numerator. We would clear fractions by multiplying by the common denominator every term in the equation. That's going to give us s equals, this is going to become an as plus b times s plus 1 plus c times s squared plus 1. Probably the easiest way to solve for this is let's make a convenient choice of s to begin. Let's let s be negative 1. If s is negative 1, this whole factor would be 0. And we get negative 1 equals c times, that's going to be 2. So c is equal to negative 1/2. To find a and b, let's make another convenient choice of s. Let's let s be equal to 0. If s is equal to 0, then we get that 0 equals 0 times a is 0, so we get b here, times 0 plus 1 is 1. Plus, remember c was negative 1/2, and then this is going to be 0 squared plus 1, which is going to be 1. And so this one will tell us that b is going to be equal to a positive 1/2. And now that we know that, just pick any other value for s to find a. Probably s equals 1 would be easy. We would get 1 equals 1 times a is a, plus b, which is 1/2, times 1 plus 1 is 2, and then we're going to have a plus, well, c is negative 1/2, so negative 1/2 times 1 squared is 1, plus 1 is going to give us 2. So we get 1 equals, distribute, 2a plus 1 minus 1, these cancel, and this will give us that a equals to 1/2. And that's going to be very important, because that's going to help us to break this last term apart. We have 5 over s plus 1 minus 3 times the following. So from our partial fraction decomposition, don't forget my negative pi s there, we know that this is going to be as plus b. Well, a is 1/2 times s, plus b is 1/2 over s squared plus 1, and then plus c, which is a negative 1/2 over s plus 1. So we're able to use our partial fraction decomposition. This works out really nice. I'm going to do a little bit of algebra to it before we try to do the inverse Laplace. Notice that every factor that's in all of these numerators is a factor of 1/2. So we can actually pull that out. So let's factor 1/2 out of that grouping. We can write it much more nicely as s plus 1 over s squared plus 1. And then minus, because of the sign, 1 over s plus 1 e to the negative pi s. We can split apart this term furthermore, and I'm going to distribute the e to the negative pi s in. So y of s is equal to, we have, that's 5 over s plus 1 minus 3/2 s over s squared plus 1 e to the negative pi s plus 1 over s squared plus 1 e to the negative pi s minus 1 over s plus 1 e to the negative pi s. And now we're ready to go ahead and find our answer. So we have y of s. It's broken down into a very nice format. So to find our solution y of t is going to be the inverse Laplace transform of this whole thing, which again we know is linear, so we can split this apart. So this is going to be equal to, it's the inverse Laplace transform of y of s, which is equal to 5 times the inverse Laplace transform of 1 over s plus 1 minus 3 halves times each of these times the inverse Laplace transform of s over s squared plus 1 e to the negative pi s plus the inverse Laplace transform of 1 over s squared plus 1 e to the negative pi s minus the inverse Laplace transform of 1 over s plus 1 e to the negative pi s. So starting off with the easiest one, we know that this one here, the inverse Laplace transform of 1 divided by s plus 1, that is simply going to be equal to e to the negative t minus 3 halves times each one of these inverse Laplace transforms. The inverse Laplace transform of s divided by s squared plus 1, we know that that's going to be the cosine. That's typically the cosine of t, but because we have the shift here of, I'm not sure why I wrote it like that. This is negative pi s. I wrote it back here too. Ooh, sorry. I thought it was kind of weird looking. E to the negative pi s. This is going to be a shift by pi. So it's not just going to be cosine. It's actually the cosine of t minus pi. Where am I at? Yes, so cosine of t minus pi times the unit step function of t minus pi plus, now we come to this one right here. We know that the inverse Laplace transform of 1 over s squared plus 1, that typically would be the sine of t, but because of the shift, we're going to get the sine of t minus pi times the unit step function t minus pi. And then lastly, we have this one right here, the unit step function of 1 over s plus 1. We know that that would typically be e to the negative t, but because of the shift, it's going to be e to the negative t minus pi times the unit step function of t minus pi. So there we have it. This would be our solution to that original differential equation. The steps are all the same. You start off by finding the Laplace transform of both sides. We solve it for y of s. And then once you have y of s by itself, we simply apply the inverse Laplace transform. What was a little bit new about this particular example is that, first of all, we were able to write the right-hand side in terms of the unit step function. And then we had to use our theorems to not only apply the Laplace transform to a function times the unit step function, but then we also had to apply the inverse Laplace transform to functions of s that had that shift e to the negative as with them.